So let me try and demonstrate it a little bit mathematically, if I can, because I think that's an important thing to be able to acknowledge. So here I have, I'm going to copy this and get rid of that and paste it here. Let us do utility theory and demonstrate why utility theory fails for the prisoner's dilemma. And just to keep it simple, let's assume that we don't know what our partner is going to do. Let's say we just give 50-50 odds to our partner. If I say the utility of stay silent is, that's not a great font. That's better. 0.5 times, if my partner also stays silent, I get a -1. Plus 0.5 times, and if my partner betrays me, I get -3. And then the utility of betray is 0.5 times 0 plus 0.5 times -2. Let's reduce this to actual numbers. This is going to be -1, right? And this is going to be -2. Which is better, -1 or -2 from a utility perspective?
We'll go with -1.
Yeah, clearly -1 is better than -2 because it's not so negative. And therefore, utility theory says we should betray our partners, and yet we know that's the wrong answer. We should cooperate, right? Why do people say utility theory fails? Well, it did fail right here, so it seems. So I picked 0.5 because I made the assumption that the other person was just being arbitrary. And in reality, the other person is being intelligent, which is complicated, and you can't really assign that to just a number. So you're right. But imagine if we swept over possibilities. Let's do it again with the utility of stay silent is 0.1 times -1 plus 0.9 times -3. This is me assuming that my partner is going to betray me with high probability. This is me being a little pessimistic, probably a bit more realistic. What does my number come out to now? -2.8. Okay, I should have just listened to you. Just let you guys do the math. And the utility of betray is 0.1 times 0 plus 0.9 times -2. Anybody got it yet? -1.8. Which is better, -2.8 or -1.8? Obviously -1.8 is. Basically, no matter what you assign the probabilities to, and while true probability is not the same as evaluating their intelligence, there's some probability that is true in the moment, right? And yet no matter what probability you get, it still says you should betray. Here's what I claim is the failure of it. Do you see how at the time I was evaluating utility, I was evaluating the utility of my own personal interest. I was saying, what is the value to me for making these actions? But then at the time I evaluated the quality of the decision, I was doing it by saying, hey, what's the overall utility? And you see, if you change the metric in the middle of the game, of course, it doesn't make the right decision. You see that? One of the reasons utility theory is often maligned is because it's assumed that, of course, you're going to maximize your own personal utility. But in fact, that's not a valid assumption at all. There's all kinds of reasons you shouldn't maximize your own personal utility, especially in a cooperative game. So let's suppose we're doing the altruistic utility. What is the utility of staying silent? Well, if my partner is 50-50, then it's -1 minus 1 plus 0.5 times -3 minus 0, which is it -2.5? All right. Oh, you're right. Okay. Now the utility of betray is 0.5 times 0 minus 3 plus 0.5 times -2 minus 2, right? Because I'm adding both my payback and my opponent's payback, and this works out to, okay, well, there you go. Which is better, negative 2.5 or negative 3.5? Clearly negative 2.5 is better, and so it turns out that if, while computing utilities, you're actually using the same priorities that you're going to evaluate your decision with, utility theory does make the right decision in cooperative games as well as competitive games. For some reason, the game theory community doesn't seem to have fully embraced this yet, and I think they're still stuck on the assumption that utility theory means maximize your own utility. You don't have to have selfish priorities. And in fact, I'm kind of suggesting here that not only as intelligence evolves do we evolve better ways of maximizing our utilities, I think we're also optimizing our priorities. And what we're seeing right here is that we have found that these priorities yield the right answer to this game. Therefore, intelligence has just evolved correct priorities in addition to correct methods for maximizing those priorities. And I'm kind of claiming that valid priorities ought to be a little bit less self-oriented and should spread out the utility and consider everybody's utility. Is that too bold of a thing to say in a secular academic environment? I don't think so, because I think I've just demonstrated mathematically why this is the case with Prisoner's Dilemma. If you consider the overall utility, you make the right decision. I like to do it like this. When I compute utility, I say sum sub I of utility for everyone, but then plus 0.001 if I is me. Okay, that's pretty awful pseudocode here. But here's what I'm saying. My version of altruism, and this is, there's a lot of different definitions of altruism. Some people say altruism is suppressing your own self-interest for the good of the whole. That's kind of a destructive version of altruism, and I don't think that's a productive or good way to do it. Other versions of altruism say, hey, you just consider the sum of everyone's utility. I say, add a little bit more for yourself. Take care of yourself first, but then also consider everyone's utility. Is that really altruism? I don't know, maybe not. But whatever you call it, if you maximize that, it turns out that this gives you the right answer in Prisoner's Dilemma. It gives you the right answer in chess as well. Why? Imagine I'm playing mini-max while always making the decision, maximize my own personal utility just slightly more than my opponent's utility.
Oh, that's what you do.
Do you see what that does? It means when I'm playing chess, I say, oh, I'm so sorry I have to take your queen, but it's just my utility matters just a little bit more than yours, and so overall this is positive for me. And if my opponent plays the same game, we can still play very intelligent competitive games even though I have compassion for my opponent. You see that? And yet, if I follow this same priority, it also does the right thing in Prisoner's Dilemma and every other game. I've never found a game where maximizing the total utility plus mine just an arbitrarily small amount more doesn't make the right decision. Therefore, I have some slight, by the way, this is not some kind of, don't memorize this for a test or anything. This is Dr. Gashler's untested hypothesis. And I'm only throwing this hypothesis out there, and I'm not telling you this is a theory or truth or anything like that. I'm just telling you that I speculate that prioritizing everybody's utility plus yours a little bit more might be the long-term product of the evolution of cooperation, because it just seems to make the right decisions when you apply utility theory to arbitrary games. And if that's the case, then that's an important thing to know if you're going to be considering how to make decisions in arbitrarily complex environments. All you do is say, hey, this is the right priorities, now just apply the right technique, which is basically always utility theory, and voila, now you can calculate the best decision to make that will maximize long-term utility and so forth. Cool? All right, somebody will probably come back and challenge me next time because, it's just an idea and I don't know that it's well established. But there you go, it seems to work. Now let me qualify it a little bit. Whenever you say something, you got to point out why it's not true. So turns out tit for tat is not the optimal strategy in iterated prisoner's dilemma. There is a better one. The better one is actually anticipate what your opponent's going to do and then make your decision intelligently. You see how that's more intelligent? The problem is it's hard, because anticipating your opponent is hard. It's really hard to see the future, and it's really, really hard to anticipate what intelligent things are going to do, especially if they're as intelligent as you are, because then they're applying the same amount of computation into predicting their futures. So you see how it's almost impossible to anticipate what an intelligent being will do? It's an arms race, and presumably the arms race requires more computational power than you have to work with. Yeah.
Also, if you're running a giant tournament for how people are going to be designing programs to get the best scores in a prisoner's dilemma thing, aren't the competitors playing a giant form of the prisoner's dilemma? By what if literally everybody uses an algorithm that would only, stay silent forever? Then
Yeah.
So isn't that just an enormous game of the prisoner's dilemma?
It is, and very much by design. So yeah, in fact, this is kind of what we're at some point we're getting to the core of intelligence here when we start to realize where AI reaches society's decision-making abilities, aren't we? And so I think game theory is this very fun playground to play in. But yeah, basically, tit for tat makes the assumption that it's impossible to foresee the future, and the best predictor of what our opponents will do next time is what they did last time. Is that a valid assumption?
No.
Nope, it's not, but it's as valid as any assumption we've got. So basically, because it's as good of a predictor as we've got, tit for tat works really well. If you can predict what your opponent will do, then it turns out you can be more intelligent than tit for tat. And someone did eventually submit something that beat it, but it leveraged what some people might call cheating, which is that it carried information back from playing multiple games and started, leveraging weird little details to figure out what the other opponents were doing. There's also something called an end game. Anybody heard of an end game? You know what an end game is? Yeah.
Chess, it's sort of like once most of the pieces are off, and you're sort of down to the king and the pawns, and maybe a couple pieces.
Yeah. It turns out that when the game is almost over, cooperation isn't necessarily the right thing to do anymore. So imagine that we're going to play exactly 1,000 iterations of the prisoner's dilemma. Well, tit for tat is the right strategy until the 999th iteration, right? And then what do you do on the last iteration?
You betray.
Always betray, because you can get that little bit of extra juice out of the game, right? And so tit for tat plus betray at the end is slightly better. But now think about that recursively. If that's the case, if you know that's the case, and your opponent knows that's the case, and you know your opponent knows that's the case, you know your opponent's going to betray you on the last iteration. And now you have a little bit more information than tit for tat has, right? So what do? You betray them on the second to last iteration of the game. And now all of a sudden you're thinking, recursion, and now you have the always betray strategy. And yet the always betray strategy isn't the best one. What's going on? Right?
Have it arbitrary how long it goes.
Yeah, so that's what they do, is they pick a random number and then they iterate for that number of games. So you don't know when the end comes. And then it turns out that it's best to just always play tit for tat. Except, if you can have real hardcore intelligence that can actually model the opponents well enough to anticipate what they're going to do, then you can make even better decisions than tit for tat. So the universe is complicated, I'm sorry. But in fact, that's actually kind of fun. It's the playground we get to play in. So there you go. We've analyzed a little bit of game theory.